All right, children, so this is going to be our 4-2/3. It's going to be one big lesson combined into one. So this lesson is going to be kind of gnarly. I'm going to go a little bit fast. Some of it's just review, and some of it's just really brief just because you need to see it once. The do now is pretty straightforward. I'm not going to linger on that. So what we're going to be studying in this lesson is going to be absolute value. Here, let me. Okay, I had to switch mics there because that other mic doesn't work very good. So hopefully this video doesn't screw up as far as sound. Anyway, so what we're going to be studying is step, which is a kind of piecewise function, and absolute value functions and their transformations. Okay, the transformations part will be on a Google form that Miss Roundtree made for us. The rest of it's going to be in this lesson and in this video. And, well, before I get too far ahead of myself, so here's my EQs. What are number sets and what letters represent them? What is a step function? How do you express an absolute value function as a piecewise function? And in what way specifically can we perform transformations on absolute value functions? Okay, so number sets, this is just a brief review. I'm not going to stay on this page for very long, but you've got all different kinds of numbers. So the most specific numbers are your natural numbers, also known as your counting numbers. All right, so these are your numbers that we count with. 1, 2, 3, on and on and on and on. We do not include 0 in the natural numbers. Okay, it depends on what book you're reading, but most literature in math doesn't include 0 in the natural numbers, as far as I remember. Okay, your other kind of numbers, right outside of that, are called integers, and integers actually encompass the natural numbers. Okay, so integers include the natural numbers. I just cannot draw an oval. Anyway, integers are natural numbers and their negative counterparts, including 0. So 1, 2, 3, on and on and on, right? And 0 and on the other way. Okay, another name for these guys that you may have heard is the whole numbers. And before I forget, so n represents your natural numbers. This fancy looking z represents your integers. Okay, so to reiterate one more time, integers are natural numbers and their negative counterparts, including 0. Okay, then we've got an even broader type of number called rational numbers. Okay, rational numbers include integers, they include natural numbers. Okay, what rational numbers are exactly what their name implies. They're numbers that can be expressed as a ratio, or more specifically, a fraction. Okay, any number that can be written as a fraction. So for example, the number 4. Well, why the number 4? If I take the number 4, I can rewrite it as 8/2, which is a fraction, or 4/1, or whatever, right? That would also include the number, I don't know, 16/5. That's a rational number. Another rational number would be -18. Another rational number would be -1/2, and so on and so on and so on. Anything that can be written as a fraction, anything that can be written as a fraction is called a rational number. Okay, now we move on to real numbers. Okay, real numbers include rational numbers, integers, and natural numbers. Real numbers also include irrational numbers, which I'll get to here in a second. But real numbers are literally every single number you have ever studied in school. All right? Any number you've ever come across, whether it's pi, whether it's the square root of 2, whether it's 15, whether it's 1,000, whether it's 1/2, whether it's -13/4, okay? Anything, any number you've ever come across is a real number, okay? And we use R to represent that, okay? And I forgot to mention we use Q, obviously, to represent the rational numbers, okay? Now, irrational numbers. Irrational numbers are real numbers, but they aren't rational. They're not integers, and they're not natural numbers. Irrational numbers are numbers that cannot be written as fractions. They are irrational. Okay? So, numbers like pi that give us decimals that go on and on and on forever, those are irrational. The square root of 2, likewise, the square root of 3, the square root of 5, and so on and so on and so on. Anything that has a decimal that just goes on and on forever is an irrational number because we can't express it as a fraction. No fractional. No fractional. Okay? Then you've got your complex numbers and your imaginary numbers, which we'll study later on in the year. Okay, so really briefly, we're going to cover an important type of piecewise function that we didn't get to cover last class, all right, and that is called a step function. Okay, and you're going to see why here in a second. Okay, so it's called a step function for a reason. So, graph the equation f of x equals, well, it equals -2, so we're saying f of x equals -2 based on this domain restriction, x is less than -3. So here's -3. If x is less than that, f of x equals -2, which is right here. Okay, so that's going to be an open circle, right, because of this symbol we've got here. It's going to be an open circle, and it's just going to look like this. It's just constantly, keyword there is constantly going to look like this. It's going to be a horizontal line because f of x will always be, constantly be, -2, right, given this domain restriction. Okay? Now, what about this guy? Well, f of x will equal 1. It'll equal 1 if x is greater than or equal to -3 and less than +2. Okay? So, let's look at -3 again, right here. And f of x is going to be 1, and we're going to use a closed circle because of this symbol, because of this less than or equal to. We're going to use a closed circle. It'll equal 1 all the way until we get to x is +2. Well, then are we going to use an open or closed? We're going to use an open because of that less than. So we are not going to include +2. Okay? And all in between here, f is constantly equal to 1. Okay? And now you can kind of see it's starting to look like a set of stairs, okay, which is why they're called step functions. I'll use red this next one. So on this last one, f of x equals 3 for this domain restriction. X greater than or equal to 2. So it equals 3. So we're looking at 2. X equals 3, and that's going to be a closed circle because of this symbol here, greater than or equal to. And it's going to give us a constant value for f of 3. Okay? So in a nutshell, that is exactly what step functions are. Step functions are just piecewise functions that give us constant values for f, depending on their domain restrictions, such that they look like steps. Okay? You get the idea. That's why they're called step functions. Okay, so interval notation. We're going to get a little more detailed with interval notation. And when I say interval notation, I mean parenthetical notation, using parentheses. Okay? So we're going to look at this really quickly. Not going to linger on it too long because I don't want this video to be insanely long. So looking at this piecewise function, f of x, we have 3 domain restrictions and 3 function rules depending on those restrictions. The first question we're asked is, what is our domain using inequality and interval notation? So our domain using inequality notation, well, if we look at the graph, that we've got here, right over here, I still don't think you guys can ever see my mouse in these videos, but if we look at the graph right over here, okay, x doesn't seem to be restricted by anything, but looking at the actual domain restrictions, okay, right here right here, right here. We're excluding something. Okay, and what it is that we're excluding in the domain restrictions is we're excluding 3 here because x is less than -3, right? So we would say negative infinity is less than x is less than -3. Well, then when we look at the next rule down, when we look at the second rule that we've got, and let me use this gray, maybe this will be more neutral. When we look at this second rule that we have associated here with this domain restriction, okay, we see that we are going to be excluding -3 completely. Okay, so we would say negative infinity is less than x is less than -3, or -3 is less than x is less than +3. So that means I would have an open circle here and an open circle here from both of these. Okay, so that means we are not touching -3 and we're not touching +3, at least not yet. Let's look at this last domain restriction in this last function rule. So it equals negative absolute value of x plus 4 if 3 is less than x. Okay, meaning x is greater than 3. So for x greater than 3, well, even down here, it's another open circle. Okay, and what we would write is another or, so we have 2 ors here, another or basically saying that 3 is less than x is less than +infinity. Okay, and again, what we're basically doing, we're basically saying that x does not equal -3 because we excluded it here and here, right? We had that open circle coming here from this direction and an open circle going here from this little parabola. Okay, we also would say that x does not equal +3 because when we're going this way, we have an open circle here, and once we start going this way from this other direction of +3, same thing, we have another open circle. So we're basically just not touching -3 or +3. So another way to write that is to simply say that the absolute value of x does not equal 3. So that's one way to think about it. That's working smart and not hard. How would we say that with interval notation? Well, and I think I'm going to skip number 2. I'm not going to worry about the range. I just want to motivate the use of a union. But anyway, in interval notation, so when I say interval, I'm talking about parentheses. Okay, parenthetical notation. So how would I write this guy? In parenthetical notation? Well, I would say -infinity, comma 3, and I would use a curved bracket because I'm excluding 3. What do I do for this or? I can't literally write or any kind of way with parentheses, right? Well, that's where this little u thing comes in. This little u thing is called a union. Okay, so I would say open parentheses, -infinity, comma 3, close parentheses, union, which is like my or, and then I'm going to go ahead and do this guy here. -3 is less than x is less than 3. So -3, comma 3, close parentheses. We're excluding this 3 again. And we have another or, so that means I have another union. Okay, and now I'm going to write my parenthetical notation for this part of the domain, which is going to be 3, comma, +infinity. Okay, so there's our other union, or our other or statement there. Okay, and we're not going to worry about number 2 right now. We're not worried about that. Okay, so now we've got some guided practice to go through. In the video, I'm going to go ahead, and in class, I'm going to go ahead and do the evens. I'll leave the odds for you to do. So I'm going to do 2, 4, and 6. You're going to do 1, 3, and 5. And so that I don't forget which one to do, I'm going to go ahead and circle them. So explain what each notation means literally, which is a fancy way of saying in words. Okay? So what do I have here? I have y bar, y epsilon z, 0 is less than or equal to y is less than or equal to 12. Basically what I'm saying here is that our range is that y is an integer, okay? That's what this little z stands for. Y is a part of the set of integers such that, so y is an integer such that y is greater than, I can't spell, that's supposed to say greater than or equal to 0 and less than or equal to 12. Okay, so that's pretty straightforward. Okay, sorry about that. That was, yeah, got interrupted by a phone call from my wife. Anyway, so y is an integer such that y is greater than or equal to 0 and less than or equal to 12. Okay? Can y equal negative 1/3? Can y equal negative 2? I'm going to leave that part to you. Okay? Number 2, what am I saying here literally in words? So I am saying, and since we aren't given a variable, we'll go ahead and use x. Okay, but what I'm saying is simply this, and sometimes it helps to rewrite the parenthetical notation as inequality. So negative infinity, and we have a curved bracket, so that means we're being exclusive, right? So we use a less than symbol. So negative infinity is less than x is less than negative 2. Or, that's what the union means, right? Or negative 2 is less than x is less than 25. Again, I know it's just a less than symbol because of the curved brackets. Okay, so how would I read this out loud? Well, x, and if we're not, remember I told you, if we're not given anything specific about what set this belongs to, so on number 2, I was told specifically it's on set z, the integers, right? On number 4, I'm not given that. So we're going to go ahead and assume that x is real. It's a real number. Okay, x is a real number such that x is less than negative 2 or x is greater than negative 2 and less than 25. Okay? So that's how I would write that out literally. Now let's look at number 5. Write the function's domain and range using interval notation and more specifically parenthetical notation. So our domain, so basically you would throw this into Desmos, and this is just your run-of-the-mill parabola. Okay, so here's your x-axis, y-axis, and your y-intercept is going to be there at the origin, and it's just going to be a parabola, just like that, except less stupid because it's made by a computer and not by my crappy hand. Anyway, so what we would say about x, well, is there any restriction placed upon x? No. Okay, so what we would say for our domain, we would simply say in parenthetical notation that x can be going on and on and on forever to negative infinity and going on and on and on forever to positive infinity. Basically, x can be all real numbers. Okay? Now, what about for our range? Well, our range, obviously, is restricted a little bit, right? Y has to be greater than or equal to 0. Y can't be negative because that's impossible. You square anything, you always get a, well, at least real numbers. You square anything and you always get a positive answer. So what we would say is I used the wrong bracket there. We would use a square bracket, right? Because we're including 0. We're including 0. So we would include 0 and go on and on and on upwards to positive infinity. Okay? So the last one I'm going to do, and I did the wrong one. I circled 5 when I said I was going to do evens. What's the matter with me? I guess I have to do another one now. Well, in class, I'll be sure and do one of these other ones for you. But like I said, I want to keep this video short. Yeah, it's 8:40 at night, and I'm a little bit worthless. Okay, so consider the functions f and g. Okay, so right now we're going to talk about the absolute value function, and we're going to define it in piecewise. Okay, so here's f, here's g. Okay, I'm asking you to create t-charts and use Desmos to graph both f and g. Okay, and I'm also asking you, well, what do you notice? Okay, so I want you to do that on your own. Go ahead and figure it out. And good Lord, if you don't remember what a t-chart is, okay, like all you goofballs in the do now the other day, oh my goodness, it's just you're plugging in values of x and y. Okay, and I'm telling you right here, start with -5, and you're going to end. So you're going to go -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. Okay, you're going to make a t-chart for all of these. Okay, and you're just going to plug those numbers in and see what you get for y. So -5 plugged into here, I would use this domain restriction because -5 is less than 0. So you would have -5, that gives you +5. -4, that gives you +4. And this is going to give me 3, 2, 1. And then when I get to 0, of course, that's going to be 0. And I would be using this domain restriction because 0 equals 0, right? And when I plug in 1 for x, of course, I'm going to get 1 for y, 2, 3, 4, 5. Okay? I want you to do the same thing for g of x. So this one was f of x. I want you to make a t-chart on your own, your big boys and girls, for g of x. Okay, going from -5 to +5. All right? It took me like 30 seconds. You can do this. Okay. So I'm going to do the evens this time. Or actually, I'll do the odds. We'll do 5, 7. I'll do just 5 and 7. 9 you can answer on your own with your own big teenager brains. Okay, so define the following absolute value functions in piecewise. Okay, and you're going to use Desmos to help you wrap your head around it. Okay, I am not going to use Desmos because, yeah, it's going to be too complicated to edit that in with the video editing software, and I've already been here a long time. So anyway, so looking at this, okay, how would we define this as piecewise? Well, if we're looking at this g of x here, if we're talking about absolute value, you have to remember, so if we have g of x equals -3 times absolute value of x plus 1, right? That's the same thing as saying what? Well, that's the same thing as saying g of x equals -3 times negative x plus 1. You ought to remember doing this from lesson 1-3. Or g of x equals -3 times just regular x plus 1. Okay? And we have to consider something. What would make this in here be 0? And in here, right? So basically right here, what would make this be 0? What value of x would make this be 0? Well, the answer is -1. Okay? So the way we're going to define that in piecewise is g of x equals, and then we're going to use our cute little curly bracket thing. It's going to equal, so if I go ahead and distribute this 3 in here, this would become +3 times x plus 1. Okay? That's going to be if x is less than -1. Okay? Or if you're used to seeing it, I'll just leave it like that. So that's going to be for x is less than -1. Okay? it's going to be this guy, negative 3 times x plus 1, if negative 1 is less than x. Okay? And again, if you don't understand why I got what I got, use Desmos, and I promise it'll make perfect sense. Okay? Number 7, I'm going to go ahead and start erasing. If I can find my eraser. So number 7, we've got something a little bit uglier, which is good because, you know, it'll freak you out less when you see number 8. So again, I'm going to write it out as m of x equals, okay, so it's absolute value. So that means it's going to be negative 1/2 times x minus 4, or m of x can equal positive 1/2 times x minus 4. Okay? And again, what value of x is going to make this be 0? Well, your answer there is obviously 4. So that's going to be important when we do the actual piecewise. So m of x, let me just erase that. Next time we click the save button. M of x equals negative 1/2 times x minus 4 if x is less than 4, right? And it equals positive 1/2 x minus 4 if 4 is less than x. Okay? And again, you'll see why exactly in Desmos. All right? So hopefully that video was short and sweet enough. And here's another look at our EQs. And hopefully we've got everything we need to answer those. And if you need anything, obviously shoot me an email. That's all I got for you, children. Goodbye.